Hello students, good day. I hope all of you are safe. In the previous lecture, we discussed memory management in journal, a concept that is used to decide how logical addresses that are present in a program can be mapped onto the physical addresses that are present on the main memory. In the today's lecture, we will discuss how different processes are stored on the main memory. For this, we will discuss the contiguous memory allocation, uh, where a process is stored onto the main memory in one chunk. And within this contiguous allocation, we will discuss fixed partition as well as the dynamic partition of the main memory to accommodate multiple processes. And within dynamic partitioning, we will discuss multiple algorithms, including first fit, best fit, and the next fit. Contiguous allocation is a technique that allows a process to be loaded onto the main memory in one chunk. So bytes of the main memory are allocated to a process so that the instructions and data associated with that particular process can be stored in one chunk. As we already know that main memory is shared among multiple processes. So usually we have two different partitions of the main memory. The first one is reserved for the operating system, where the kernel of the operating system is stored, and the other partition is reserved for the user processes. And all of those user processes, they share that main memory among each other. Also, as probably you remember in the previous lecture, we discussed the concept of base register, limit register, and the relocation register, where they are used to protect one user process against illegal access from the other processes. So the base register contains the value of the smallest physical address that can be accessed by a process. Likewise, the limit register contains the largest possible address that can be accessed by a particular process. In contiguous allocation, the main memory is divided into some partitions, and each of these partitions is eligible to accommodate a process into it. And if some of these partitions are free, we call them holes. So hole is a block of available memory where we can load a process. So when a process arrives in the system, it can be allocated to a hole that can accommodate this process. And once a process completes its execution, it leaves the main memory, and the hole that was earlier occupied by this process is now again available to accommodate other processes. So in this way, the operating system maintains information about the allocated partitions and the free partitions that we term as holes. So at the same time, operating system maintains information about the allocated partitions as well as the free partitions. It is also interesting to note that the number of partitions can be fixed in some systems. Therefore, the number of processes that can run at a particular time in a system can be defined by the number of partitions. So we can say that the degree of multi-programming is sometimes limited by the number of partitions that are available on the main memory. So over here we have a pictorial representation of the same concept. So you can see that on top of this main memory we have our operating system, and the leftover memory is available for the user processes, and these are the allocations of multiple processes onto the main memory, having some holes as well. So you can see that we can have different size of processes that can be accommodated anywhere onto the main memory, some partition that is allocated for the user processes to be loaded. When we have memory allocations, there are two types of partitions that are possible. The first one is the fixed memory partitions, and the second one is dynamic partitions. In the fixed memory partition, if we have this user space, or the space where the user processes can be loaded, so this space can be partitioned in fixed size chunks. So for instance, if this space is 100 megabyte, we can divide it into 10 chunks of 10 megabyte each. On the other hand, in dynamic partitioning, we do not partition the space in some static manner. Rather, dependent on the size of the process that is arriving in the system, we partition this space accordingly. So it is possible to have different size of partitioning in the main memory, in the area of the main memory where user processes can be loaded in the dynamic partitioning method. So over here we have an example of fixed partitioning. Let's suppose that we have a main memory of size 32 megabyte and it can be partitioned into chunks of 4 megabyte each. So a total of 8 equal size partitions will be there on this main memory. As you can see that there are 8 partitions on this main memory, so the number of processes that can be loaded onto this main memory at any particular point in time can be limited by 8. So over here we have some challenges that we have to face while dealing with fixed partitioning. So the first challenge is that it is possible that the size of the process is larger than 4 MB, in which case we have to divide our program into overlays, and programmers may need to write their code using overlays, writing them in a mutual exclusive fashion so that we do not have overlapping instructions or data. In the same manner, if the program size is too small than the partition size, then we will have some wastage of memory. So in this example, where we have one partition of 4 MB, what if we have a program which is of 100 kilobytes only? So the rest of the space will be wasted. This wastage of space within a partition in the fixed partitioning method is termed as internal fragmentation. So internal fragmentation is a concept which applies on the wastage of memory in the fixed partitioning method, where if the size of a process is smaller than the size of the block, then the remaining memory will be wasted, and it is termed as the internal fragmentation. So over here we have pictorial representation of this internal fragmentation. So you can see that we have 3 partitions in here, and these are the sizes of the processes that are loaded onto these partitions, and this yellow space is the unused memory. So you can see that it is possible that if we have like unused space of more than 5 or 6 MB present on a main memory in terms of internal fragmentation, but even at the same time it is also possible that we may not be able to allocate this space to any other process. So the space is available on the main memory, but it is internal to the partitions, so it is not available to be allocated to other processes. So that is why this space is wasted. This phenomenon is termed as internal fragmentation. The second method of partitioning is dynamic partitioning. As we know that in fixed partitioning we have either internal fragmentation or The developers may have to write their code using overlays. So both of these conditions are not very useful, or we may not say them ideal conditions. So in order to avoid these disadvantages and to utilize the main memory in the probably more efficient way, dynamic partitioning of the main memory was proposed. In this partitioning, we have variable size of the partitions, as well as the number of partitions can be different, and they are dependent on the incoming process. So if the incoming process is larger in size, for example, it is 10 MB, so we can allocate a partition of 10 MB to this particular process. On the other hand, if an incoming process is of 1 MB, we can allocate a partition of 1 MB to it. So in this way, we can allocate the exact amount of memory that is required by the process. So this avoids the disadvantages that we have to encounter in the case of fixed partitioning. So let's have its example on the coming slide. Over here we have a diagram to reflect this concept of dynamic partitioning. So in this example we have a main memory of 64 MB, where the first 8 MBs are allocated to the operating system, and the rest of 56 MBs are reserved for the user processes. So now assume that we have a process coming into the system with the requirements of 20 MBs. So these 20 MBs will be allocated to this process. Further, if we have another process requiring 14 MB of space that enters the system, we will allocate 14 MBs to this process. Moving on, if we have another process requesting 18 MBs of space, we will allocate a partition of 18 MBs to this process 3. In this way, you can see that there is no wastage of memory when we have these three processes in the main memory. Now, let's assume that after some time, P2 completes its execution and it leaves the system. So we have this hole available that is of 14 MB. After a while, we have another process that requires 8 MB of space, so we allocate a partition of 8 MBs to this process P4. After some time, P1 completes its execution and leaves the system. So now we have these three holes present in the system. The first one is of 20 MBs, the second one is of 6 MBs, while the third one is of 4 MBs. Now after some time, if we have process 2 coming into the system one more time requiring a main memory of 14 MBs, we will allocate a 14 MBs partition to this process. Now again we have three holes in the system. One is 6 MBs, second one is 6 MBs, and the third one is 4 MBs. So now let's suppose that if we have a process that requires 8 MBs in total, we cannot allocate a particular partition to that process, even though at this time we have the 16 MBs of space available to us. But still we are unable to allocate because it is not contiguous. So this concept where we have holes present in the memory and the memory space is available, however, as it is not contiguous, we cannot allocate to a process. This concept is termed as external fragmentation, and it happens in dynamic partitioning method. Along with the problem of external fragmentation, we have another challenge in dynamic partitioning. So let's suppose this is our new state of the memory, and we encounter another process that requires 4 MBs of space. Now we have 6 MBs, 6 MBs and 4 MBs. What do you think? Which of these holes should be allocated to this process that requires 4 MBs? Some of you may think that it should be 4 MBs, which is probably the best fit for this process, while some of you may argue that it should be this 6 MBs because this is the first hole that we encounter from the start of the main memory. So there can be multiple approaches to allocate this process to the holes that are not in any order. So what should we do in such condition? So to solve this, we have several methods that are available to us in order to decide if we encounter a process in a running system, which of these holes should be allocated to that process if we have different partitions available throughout the main memory. Among them we have first fit, we have best fit, and we have next fit. These three algorithms are used to solve the problem of dynamic storage allocation in dynamic partitioning of the main memory. So the first algorithm is first fit. This algorithm suggests that you should start traversing your main memory from the beginning, and whatever first hole you find that is big enough to accommodate that process should be allocated to that process. So the first hole that is big enough to accommodate a process should be given to that process. This suggestion is due to the fact that we can traverse our main memory from the start, and in this way we may get the first hole in an efficient manner instead of searching through the whole partition. However, on the downside, it is possible that after utilizing this first hole, the remaining external fragmentation or the remaining memory that is left over after allocation of the dynamic partitioning to this process may increase the amount of external fragmentation in the system. The second method is best fit. This method proposes that you should traverse the whole main memory and keep track of all the holes that are available on it, and you should allocate the smallest hole that is big enough to accommodate a process to that particular process. So the process will be fit into the best possible hole that is relative to the size of this process. So a memory hole that can accommodate the process in the best manner should be allocated to that process. And the advantage of this method is that it leaves the smallest amount of memory behind, which means that the external fragmentation in this case will be minimum. However, on the downside, you have to traverse the complete main memory every time when you encounter a new process, which requires a lot of time. So these are some advantages and disadvantages associated with the best fit method. The third method is next fit. In this method, you keep track of the pointer where you allocated the main memory to the previous process, and once you encounter a new process, you just start your searching from that very pointer towards the end of the main memory. The motivation behind this method is that if you start searching from the beginning of your main memory, every time when you encounter a process, it is possible that you are required to traverse a lot of memory before you find some hole, because the initial memory is already allocated to some other processes. So if you keep on moving in the forward direction, you will more likely to find a hole that can accommodate that process. So this can be seen as an optimization on the first fit algorithm. Here we have a summary of the three methods that are used in dynamic storage allocation. The first method is first fit, where we begin our search for a hole from the start of the main memory. and the first hole that we find is big enough to accommodate that process is allocated to that process. The next method is best fit, where we traverse the complete main memory and we keep track of all the holes that are available on the main memory. And the smallest hole that is big enough to accommodate that process is allocated to that particular process. This gives us the minimum amount of leftover memory. The third method is next fit, where we keep track of the previous pointer and we start our search from the location that is allocated to the previous process, and we start our search from there and we traverse the main memory towards the end of it. A motivation behind this is that it is possible that the beginning of the main memory is already occupied by other processes. Once you complete your searching towards the end of the main memory, you can again start it from the beginning if you are unable to find a hole that is big enough to accommodate that process. As we have discussed earlier, that in dynamic partitioning, we allocate a partition that fits the requirement of the process. So there is no internal fragmentation in dynamic partitioning. However, it is possible that during running of a system, we have multiple processes coming in and going out of the system. Then we may have some holes in the main memory where we may not have contiguous memory available to accommodate another process, but the memory is available in small holes. So for instance, in this example, if we have a hole of 6 MBs, another hole of 6 MBs, and another hole of 4 MBs, a collective of 16 MB space is available, but it is not in a contiguous manner, so it cannot accommodate a process of 8 MBs. This wastage of space that is external to the partitions is termed as external fragmentation. So internal fragmentation is the wastage of space that is internal to the partition, and external fragmentation is the space that is wasted outside the partition. In both of these cases, this space is not being used by other processes that require some space in the system. So internal fragmentation happens in fixed partitioning, where the allocated partition size is larger than the size required by a process. So we have some space wasted within a partition which cannot be used by other processes. This is internal fragmentation. In external fragmentation, we have space available on the main memory, but it is not contiguous, so it cannot be allocated to a process. So again, it is not available for other processes to be used. We can reduce this external fragmentation by a process of compaction, where we shuffle the memory content of different processes so that they cover up all the free space, and the free space is now available in one large block at the end of the memory. So this compaction is possible in dynamic partitioning, and it is executed once the system is running. So internal fragmentation is specific to fixed partitioning, while external fragmentation is refers to the wastage of space in dynamic partitioning. All right, students, so that is all for today. In today's lecture, we discussed how different processes can be stored on the main memory. And under this, we discussed a method which is contiguous allocation. In contiguous allocation, we discussed fixed and dynamic partitioning. And we saw what is internal fragmentation and internal fragmentation in case of fixed and dynamic partitioning respectively. In the next lecture, we will discuss a method of non-contiguous allocations, that is spacing. Alright students, please take good care of yourselves. Stay safe. Thank you.